Good afternoon, everyone. So we'll start with the afternoon session. For today's session, we have Dr. Manoj and Praseedha from Zeiss Microscopy, and they will take us through the APEER platform. So Mridula will now introduce Dr. Manoj.
Good afternoon. I welcome everybody to the afternoon session of the final day by Image Analysis. So I have the pleasure of introducing Dr. Manoj Mathew. He has obtained his bachelor's and master's degree, master's degree in electronics engineering and photonics from Cochin University. He received his PhD in biophotonics with a thesis on neuron guidance and nano neurosurgery using optical tools. After completing his postdoctoral fellowship in Gothenburg University in Sweden, Dr. Mathew joined NCBS as to manage the light microscopy facility. In addition to managing the facility, he was also involved in designing imaging systems and automation tools and in many collaborative projects with the industry. Dr. Mathew then joined Zeiss in 2018 as a light microscopy specialist. In this role, he provided application development and support for advanced light microscopy systems to Asia Pacific region. He is currently the business development manager for digital services and software for the APAC region. He creates and executes strategies, develops resources and competencies, designs solutions, and explores creative ideas to promote digital innovation, software, and allied services. So this is about Dr. Manoj Mathew. I would also like to introduce Dr. Praseedha now. So a little about Dr. Praseedha. Ms. Praseedha Krishnan Aniyath obtained her bachelor's degree in electronics and communication engineering from Calicut University. She obtained her master's degree in electrical engineering from IIT Bombay. She started her career as an image processing intern at Center for High Performance Computing, NTU Singapore, in 2013. She continued her work in NTU as a research engineer till 2014. In early 2013, she joined the industries as an image processing engineer in Strata Systems Private Limited, Singapore. Her primary role in the company was to develop and enhance image processing algorithms for airport and runway surveillance systems. She joined Carl Zeiss Private Limited, Singapore, in September 2020 and currently supports the Zeiss APAC digital solution teams in implementing software system image analysis and automation projects. So I welcome you all to both the talks. And as for some instructions for the participants, please mute and switch off your video until and unless instructed. You can type your questions in the chat box and they will be taken up by the volunteers at the end of each talk. Yeah, Dr. Manoj Mathew, please, you can start your presentation.
Yeah, thank you, Mridula, and thank you, team. Am I audible?
Yes, Dr. Mathew, you're audible.
Can you see my screen?
It still hasn't appeared in our. I can't view your screen yet.
Okay, I'm trying to share. Let me see what's going on. How about now?
Yes, it's appearing.
Right. Yeah, thanks, Mridula. Thanks, the team at JNCASR for organizing this workshop and also having us here. So what we are going to do here is a little bit of a continuation of what Dr. Srini presented in the morning. So his talk was specifically about denoising and using machine learning for denoising. What we are going to introduce here in this workshop is a platform where several tools can be used, including image analysis and machine learning. So I will start with a bit of a small presentation, and then we go to the hands-on part. So the tool that I want to introduce, or this platform as we call it, it's a digital platform which is called APEER. And it's a platform for image analysis on the cloud. So most of you are aware of what digital cloud is, right? Now the question is, why did we have to come up with a platform like this? This we believe is quite unique in the sense that there are probably not many, or probably this is the only platform that is fully on the cloud for image analysis. So why did we have to build something like this? So there are several reasons here. So Zeiss, has been working with microscopists for a very long time, and over this long period, we have been talking to microscopists and asking them what are their pain points. So obviously, image acquisition is one part, but the other part is what you do with the data. And obviously, you want to analyze the data and get meaningful information. And one issue we realized is that there is no single piece of software that goes take or does an end-to-end or completes an end-to-end workflow to go from image to the result you want. For example, you would usually acquire your image on some kind of a microscope software, and then that image is then uploaded to something like Image2Numbers. You do some analysis. Some of that data is probably even uploaded to Excel or Origin and so on to plot graphs and so on. So usually 3 to 4 pieces of software. That's what is required to complete a workflow. The other problem that we found is increasingly the standard tools that are available on these standard software, be it Image2Numbers or the commercial software that are available, they cannot always solve the problems that you are trying to solve, which means in many cases you need to build your own, you have to write your own programs. But then the issue is not everybody has the coding skills, especially if you look at the life sciences research environment. Not many people have the coding skills. Now, even if you have coding skills, the other problem is different people use different programming languages. So I like to program in Python. My collaborator might like to program in MATLAB. So then what happens is I might have created a program for image segmentation, and my collaborator might have done written some program to analyze binary data, and there is no way we can really collaborate unless we convert the Python code to MATLAB or the MATLAB code to Python. So this is another problem that researchers face. Yet another problem is, this is probably a lot of you are aware of, there is a lot of manual work. So let's assume you're using Image. You have to click to do the first step, then click until you finish that particular image, finish analyzing that particular image. And then when the same image comes again, you do this clicking process all over again. Some people like to write some amount of macros, but still this process is not automated. It's not a one-click solution from image to data. And all this clicking and manual setting of parameters means if different students or let's say different researchers are given a task of analyzing, they come up with different results. So there is also a problem with reproducing published results. So if you have or I have published something in a journal and somebody else is trying to reproduce it, it's the reproducing experiment itself is difficult. And once you have the right images, reproducing the data from those images gets even more difficult. And finally, there is this problem that there is one postdoc or a PhD student in every lab who is good with programming, who writes all the programs. But once that person leaves, that program is sitting on some computer and nobody knows what to do with it. And usually when such a person leaves, another person joins, and that person usually starts from scratch. So these are all problems. I'm sure it might resonate with you all. And so this is one aspect of the problems you face with image analysis. The other aspect is the hardware itself, the computational resources that you need. As image analysis becomes complex, as data becomes bigger and bigger, you need very advanced computational resources in terms of GPU, CPU, and storage. And it's not everyone that, or every facility or lab that can have access to such computational resources. Now, one solution to this in the industry, if you look at companies, what they do to address this problem is to use cloud-based solutions. Cloud-based solutions are very common now for business processing data, business data analysis. But very not so common for image processing. But now the problem with cloud is to submit some job to the cloud, you need even more programming skills. So you need not just image processing specialist, you also need a programmer who can, who is good with IT infrastructure management on the cloud, and that makes life even more difficult. So these are some of the problems that we wanted to address with APEER. So with APEER, what we tried to do was to build an image analysis platform on the cloud. So what we wanted to do was something that is very intuitive, something where the user does not have to interact with IT infrastructure or cloud management, or there are companies like Google and Amazon. I mean, you don't have to interact with all of their backend systems. We want to build something that is very visual, very intuitive, and also addresses several of the problems that I mentioned in the beginning about automating workflows, about making experiments reproducible, and sharing your workflow with somebody else. Now imagine you are doing something on Image2, and you want your collaborator or one of your colleagues in some other institution to reproduce exactly the same workflow. You cannot simply share that what you did with Image2, because, or you might have to write some kind of an SOP, or click this, click here, set this, set that, and that is never really practical. So here in APEER, you can create a workflow, an end-to-end workflow from image to data, and then share with somebody else. And that person can then reproduce the whole workflow in one click. And this makes collaborations with researchers much easier. Another thing that we wanted to do with APEER is to make this a community initiative, make it a little bit like Wikipedia. So the way Wikipedia works is a lot of that content is not created by Wikipedia itself. It's users create content and other users use it. So you have user groups, which we call as content creators, and other user groups, which are users. So if you have image analysis or image processing based modules sitting in your computers as programs in MATLAB or Python or Java or C, then you can convert them into APEER modules and share them with community at large. And then there are other people who might have built other modules, and then a third person could combine some of these modules. They can take a module that I built, combine it with a module that you built, and create a workflow. So that was a bigger picture that we had in mind when we thought about building this platform called APEER. Roshini mentioned that APEER is a free platform if you are a researcher, if you are using it for non-profit, if you use APEER for education purposes, or you're just an individual who is interested to learn more. If you're a company making profit out of this, obviously, you cannot use it for free. There are some charges applicable. So as far as today's group is concerned, I assume almost all of you are researchers in some scientific institution. So for you, this is free. And there's also a certain amount of storage that you get for free. So how does APEER work? So as you were saying, so of course you will see this in action, but to give you a bit of an introduction to how it looks like, you have these modules. So you log on to www.apeer.com, and what you can do there is to pick these modules, and these modules, each module can do a specific function. For example, one module might convert an image from one format to another. A second module might be used to enhance the contrast in the image. A third module might do some segmentation. A fourth module can be used for extracting some data. So there are a lot of these modules which you can mix and match. So if you know what is your image analysis pipeline, you can pretty much build that on the cloud. So then you take your modules, you connect them together into a workflow, and then you just run the workflow. And the results can also be viewed on the cloud. This is how it looks like. You have these blocks that get connected together. Each block is a module. So modules have inputs and outputs. So output of one module can be fed as input to the other module. And this is how you build the workflow. There are also some parameters that you might have to specify for each module. If you look at this, it's a little bit like Legos for image analysis. You have building blocks you put together into something meaningful. Now, interesting thing about APEER is each module can be built in a different programming language. So once you have a program and you convert it into a module, the process of what happens to that program is called containerization. So we use a concept called Docker. It's a technology to, and the concept of what we do with that program is called a container. So to tell it in a little bit simple way, what the container does, it encapsulates that program. So you have put it inside this container, and this container can talk to the outside world with certain inputs and outputs. So I can build a program or a container or a module using Python, another container with Java. And in this workflow, you see one module is built using Python, the second module is built using Java, another one using Image2Numbers, and so on. So as you were saying, each module can talk to the other module with inputs and outputs. And so you can connect a Python module output. So outputs are always in some standard form. It would be a text, it could be an image, it could be a CSV file, and so on. So that is something understood by all programming languages. So when you run this, it runs from left to right. When the execution reaches the Python module, the system uses a Python engine, generates the outputs. The outputs are fed to the next module. And now the system uses a Java engine to run the next module, and so on. So now the problem that different researchers use different programming languages and they cannot collaborate, that is right away solved here. And you can see if you have a postdoc or a PhD student who has a job of writing programs, that program need not exist as a JavaScript or a Python script. You can convert it to a module, which means anybody can use it. And once that person leaves, it still exists as a module, which can be used not just by you and your lab, but you can also share it with others. Now, if you are a programmer and you can build modules, you have several options. You can keep it to yourself. I mean, there are always cases where you want to wait for something to be published before you share it with somebody else. You can choose to share specifically with people. That could be people in your lab or your collaborators. Or what many researchers do, at least after they publish the paper, is to make this public. So anybody who uses or who wants to use this module can use it. And they can also try to reproduce what you did in your published work. And this is also good for many researchers who work in the image processing, image analysis domain in the scientific environment, where sometimes years worth of work ends up being just one graph in the publication. So not so much of credit as goes to these programmers. And this is also a way for them to create an account and to also showcase or to share their expertise with others. It gives a little bit more visibility to their work. And we are also working with some publishing houses to see if they can use APEER as a platform and insist that researchers, when they publish their work, rather than sharing some code, they build workflows and then share the workflow so that users can use it right away. Once you run the workflow, there are results, of course, and results are produced for not just the final result, right? So the final result is usually the output of the final module, but all the intermediate results are also available on the cloud. So if you can actually go and explore what happened in this workflow. Did something go wrong? You can explore that. And if you don't want all these intermediate results, you can delete them or choose to keep it on the cloud. Now, from what I remember, I think there is somewhere slightly over 100 gigabytes of storage available as free on the cloud. But if you need more storage, that is available on a payment basis. Obviously, Zeiss does not offer cloud infrastructure. We buy this from Microsoft. So Microsoft has cloud service called Azure. So we work with them and actually we subscribe to their service. And of course, there is some cost involved in it. Now, all the results can be viewed on the cloud on a web browser itself. So image equalization, annotations, 3D rendering, all of this can be done on using web browser itself. So end of the day, you don't need a very high-end processing system. You just need some computational tool to connect to the web with a rather good browser. Your system's performance is not really limiting the processing because it's all happening on the servers that are on the cloud. Here I have an example workflow. This is Scratch Assay. Many of you might be familiar. In the Scratch Assay, what you do is you have cells plated on some substrate. These are live cells, and you create a scratch. That means you're essentially removing cells from that region. And then the cells proliferate, and this gap gets filled up. And this is a technique used for several different studies like wound healing. So here we had built a workflow. This was done actually for one of the universities in Europe. They were doing this in a very manual way, and this is a group who were doing this day in, day out. So a lot of these Scratch essays. And PhD students would sit overnight sometimes to do this on images in a very manual way. So what we did was to build a workflow where there are several modules. One module to convert the image into a more usable format. A second module to do image enhancement, in this case, adaptive histogrammic visualization. A third module for segmentation and an analysis, and a final module for reporting. So the final report they want is how does this gap or this area increase with time, or the gap decrease with time. You could plot it either way. And this is a workflow we offered them, and they told us that now with this automation they could significantly increase the number of data sets that they could analyze on a given day. So a question that you might have is why cloud? All these functionalities, can't we build it on a system, on a local machine? That is, yes, we could, not all functionalities, but most of it. But cloud brings us several big advantages. First is you can have updates on the air. So things are not sitting on your system. So if you buy a software for analysis, how often does it get updated? Most likely every 6 months, every year, and it depends on what kind of subscription model you have with the vendor. But even then, you will have to wait, or you'd have to manually do the updates. Here, the updates happen every few weeks because everything sits on the cloud. Updates can happen, new modules are added. So for the user, the functionalities keep increasing or improving rather quickly. And this is a model that, if you know Netflix and Amazon, they're all cloud-based services. And why these services are good is because there is this continuous delivery of new features and new updates happening. Another reason why cloud is good is, as I was saying, computation infrastructure. You are not limited to a fixed computation infrastructure. Conceptually, you have infinite resources at your disposal. So when you need more resources, you can simply subscribe to more GPU or more CPU. We just have to subscribe that from Microsoft. So this makes dynamic resource allocation much more easier. And for big enterprises, you use cloud. This is the big advantage. You use computational resources as you need. If you need more, you get more. If you don't need that much, you can give it back in the sense that you unsubscribe to some of the additional resources, and on demand, you can have resources for you. So the bigger picture for us with APEER is that we could also offer these kind of services where the users can dynamically get or access computational resources depending on how much data or what kind of complexity they're looking at. Sometimes they need more GPU or more CPU that can be dynamically assigned. APEER at this point is still an evolving platform. So I would say we are still in the beta plus phase of APEER, where we have not really gone commercial with APEER. So that's why it's so important for us to work with you all to improve this platform. Another very important advantage of cloud, something that you cannot get with a local system, is parallel computation. So if you have a software like Image, usually you're processing one image at a time. So you process one image, then the next one gets processed and the next one. But on the cloud, you can have simultaneously multiple computation systems available. We call them virtual machines. You can have multiple virtual machines. And that means if you have 10 images, these 10 images can be analyzed simultaneously. You'll see in the demonstration that if you are trying to process one image, it takes slightly longer than what you will do on a local system. But if you process 100 images, it becomes much faster. So the time it takes to process 100 images is not 100 times the time it takes to process one image. Usually it is 1.5 or 2 times. So you have a significant increase in productivity and throughput because you can process images in parallel. Now, a new feature we added was for machine learning. Now, machine learning, Srini mentioned there are two ways to do machine learning. You have the more classical way, which can be done on there are standard tools available for that. But if you want to do deep neural networks or convolutional neural networks that we need for image processing and analysis, then a plug and play solution is not really there. And APEER is the first attempt to give you a plug and play solution. Plug and play in the sense that, like you build modules for analysis, now you can do machine learning on the cloud in a very simple way. You start by annotation. Annotation is a training process. Here you say green, your green is what? Your green is one type of cell, your red is another type of cell, and so on. So you are painting on web browser. It's a very intuitive process. Once you have done your annotations, you can say whether you want semantic or instant segmentation, and then you pretty much run it. So we have a very we have proprietary machine learning network. So neural networks, to build it is all about building that architecture. So we have a Zeiss specific architecture, which is based on UNet and some tools from or some concepts from Google and so on. And this is a proprietary tool, and we have had very nice results in using this. Okay, so that was the introduction to APEER, the conceptual level. Now let's go right away into the tool. So to access APEER, as I was saying, you can say www.apeer.com. So I don't know if any of you managed. So I shared the PowerPoint. So Praseedha created that PowerPoint on how to create an account on APEER. So if you have created an account on APEER and if you have access to that, you can follow along with me. So as I do things, as I show you things, please follow along so that this becomes really a hands-on session. So when I log on, I get a rather personalized user interface. Personalized means for every account, I have my credentials, I have the modules that I created and so on. Start with a dashboard. And then when you look here, there are two basic groups of things you can do. One are called public, the other one is My Lab. So public are things that are now what users have shared with others. So these are public workflows and public modules. What is the difference between a module and a workflow? I will show this as we progress. And then you have this tab called My Lab. So you have machine learning that I was mentioning before. So we will talk about machine learning in the end. The next tab is community content, where you have public workflows and modules. And the final tab is My Lab. My Lab is all personalized to what you do. So I have personally like 200 workflows that I have built, or some workflows that were shared with me or something I copied. I have modules. So these are again modules that I built or were shared with me. I have my files. So these are mostly images, but there are also other types of files. There are text files, there are zip files, there are some machine learning models and so on. So this in the file group, I can have different. Yeah, is there a question? Okay, if not, let me proceed. So in the files, you can have different types of data, and depending on the module that was created. So modules are all created by different people. So there are researchers who are building modules. There are some of our colleagues in Zeiss. There are some private companies building modules. So depending on who builds the module, some modules are designed to work with several image formats. Some modules are designed only to work with OMATIF. Some are designed to work with JPEG or PNG and so on. But in many cases, you also have a converter. You have OMATIF converters, and you can use that converter to convert your image to OMATIF, and most modules accept OMATIF. And I have a results section where the results of several of the workflows that I run are stored. There is also an option called local execution. This is not something that you might see right away. This is something that you have to specifically request, and based on your usage is allocated to you. This also requires this technology called Docker to be installed on your system. And what local execution does is it keeps all the data on your local system and does not upload to the cloud. Not very relevant to our discussion today. Okay, now let's go to my lab, and this is where you might want to follow along with me if you have already access to. Let me see if I can. I was trying to see if I could access the chat. Yeah, I think it's a bit difficult to see both the chat and to share my screen at the same time. Anyway, I was just trying to see how many of you have already logged on to APEER. Can you just give me an S or something? Is there anyone who has already logged on to APEER right now?
Yes, Dr. Mathew.
Okay.
I mean, most of the participants have logged.
Okay, that's great. That's great. All right. So if you are new to APEER, this when you go to my lab, you might not see anything to start with, right? So what I would start with is going to clicking this tab called workflows. And I already have workflows. If you are new to this, you might want to click on this tab or this strip here that says create a new workflow. So I'm going to click here. When you create a new workflow, it asks you to name the workflow. Again, things that you do here remains personal to you. Nothing is shared with anyone at this point of time. Unless, of course, all sharing depends on whether you choose to share or not. So I'm going to call this rotate images. So as the name suggests, I'm going to create a workflow where the images can be rotated by a certain angle. So this is a very simple workflow. And I say create. Okay, so it has created, let's say the bare bones of a workflow where the first module is an input module, and that comes by default. Now I have to build my workflow by adding more modules. To add a module, you see this plus button here. You click on this plus button, and it gives you a list of available modules. There are several. I can search by modules that are mine. I can search public modules. I can search modules that were shared with me, or I can search all of them. Right now, let me search public modules, and then let me go to something called geometric transformation. You can see there are two geometric transformation modules, one which I created, another one was created by the APEER team. So let me go to the one that I created. So this is called geometric transformation image. So let me repeat this process once more. So or maybe let me do this all over again. I said create workflow here. And I said that, it popped up a window, and it's asking me the name of the workflow, and I said rotate images. Let me call it 2 because I already created a workflow called rotate images. When I did this, it created the bare bones of a workflow with just one module, and this is a default module for which is an input module. To create my workflow, I have to add more modules here. In this case, I will add only one module. So this is a workflow with 2 modules. In the end, an input module and a module that will execute the rotation option. To do that, I click on this plus button. I say I want to see public modules. I click public here. And then I search for geometric transformation. And I select this one, that's a geometric transformation imaging. So when you click on a module, it tells you what this module is, a summary. So this module does several things. It can flip horizontally, flip vertically, and rotate 90 degrees, rotate by an arbitrary angle, and so on. And this module is replicating the Image2 module. In fact, the engine that is running for this module is Image2. And you have some descriptions. So this is something that comes with every module if you want to know what this module does, how to use the module, which kind of image format it supports. So in this module, I have built in what is called as bioformats, which means it supports a very large number of image formats, including the Zeiss formats, ZI. I believe the Olympus and Leica formats will also be supported if they are supported by bioformats. All right. So I click. All right, and you see this little plus button here. I have to press that plus button to add this. Again, let me repeat that step. I go to public. I say geometric transformations. And I know what it is doing now because you have seen the description. I click the plus button, geometric transformations image, and that is added as a module. Now these two now form a workflow. I have an input and I have something to do with the input. Now you see these two red buttons or the red dots here. That means that something is missing in module 1 and module 2. So in module 1, what is missing is an image. So I can say browse. And I can go to my pictures and select some picture. So in this, for this example, you can use any picture that you have. Let me see, I have this picture here. You can choose any picture on your computer. So you see, the moment I choose an input, that button went green. That means the module got all the inputs necessary. Now the second module is still red, which means I still need to give it some parameters. So let me go back. So if I click on this module now, sorry, workflow now, the workflow has 2 modules. The connections are all made now, so there is no problem with connections, but some parameters and inputs are missing. For the first module, it needed an input file that is provided. For the second module, now I'm trying to define certain parameters. What are the parameters I need to define? First, I need to choose what transformation I need to do. The transformation I want to do is rotate. So I select rotate. Now, once I select rotate, I need to mention what is the rotation angle. So I say it's 45 degrees. So I want to rotate the image by 45 degrees. Okay. The other inputs do not do anything because we have selected rotation and not translation. So X offset, Y offset don't do anything. I can also choose what output format I want. And if I want to have a specific name, I can give it a specific name, or you can leave the defaults on. can say rotate. And now you see this button has also gone green. Now I can click on this button here, say single or batch run, and it starts now running my module, running my workflow. So it's now starting with the first module. It's processing the input, means it's feeding that input image to the next module. Then she's loading that image to memory. That is done. Now the second module is running. This is a module that's supposed to rotate the image by 45 degrees, and let's see if it does that. Okay, now the second module is complete and the results are available now. See, once the workflow is complete, you see this bar here goes green, saying that image is complete. And obviously it got rotated by 45 degrees. Let's see the input. This is the input. This is what I fed into the workflow, and this is my output. Now you have a basic image visualization tool here, but if you want to have a slightly better visualization, you can click here and it opens up a window. And this window is from, so we collaborate with a company. I mean, it's now a Zeiss company called Arevis. They provide the Arevis web view, and which means visualization and 3D rendering can all happen on this web view. What can you do with this web view? So if it were a time-lapse image, you could see across the time-lapse image. If it were a multi-channel image, you could see the different channels. And if I want to zoom in, I can zoom in. I can click here. You see the channels can be turned on and off. I can do the histogram equalization. This is standard for most imaging software. Now, the good thing is you can do all this on the cloud. You don't need to do it on a local software. And select the gamma. If you were having 3D, you could use 3D. I can do annotations. I can draw these squares or say okay. So I have one annotation here. I can draw another annotation. I can choose a different tool if I want. I can put a text. I can drag it and drop it where I want, and so on. If you want to export this along with the annotation, I can use the export function. I can export this annotations as a CSV. There is an option called a JSON, but this is if you're a programmer, or you can download the annotation as an image. Okay. All right. Some options to change the background and so on. Right. I hope all of you are with me now till this point. Now, the good thing with a cloud-based image processing is you can open multiple instances of the same tool. So what I can do now, what I'm going to do now is I can create another instance of here. I can create one more. I can create one more. I can go to my workflows. I can create this, take this workflow, open workflow. And I can change this image to something else. So I have a lot of image on my, so every time you upload an image, it gets uploaded to the APEER cloud storage. So I can select an eCell image here and say run. I can go to my next instance, open this workflow again. Open workflow. It says I have one workflow running. This time I can give a different image here. Test if I run this, I can go to my workflow again. So the point that I want to show here is that here we are really exploiting the feature on the cloud that multiple instances of the same tool can be run. This is probably something you cannot do in a tool like Image2, where you'd wait for something to finish before you run another instance of the same workflow or same processing function. So here, let me select another one. Okay. You see one workflow is running. So all the other workflows that I did were already completed. So now what I can do is I can go and take maybe even open another instance of APEER because I want to view the results. I can go to my results, and here you see all these rotate instances that I ran are available here. So let's see what this was. You can see this image was rotated 45 degrees. Windows annoying. Sorry, I have a bit of an issue with this sharing window popping up. Let me go back to my results. Open another of my result here.
Dr. Mathew. Hello.
Yeah, tell me, please.
Dr. Mathew, there are some questions in the chat. Should I read it out now?
Yeah, I mean, it would be great if you could read out. For some reason, I am not able to see the chat with my sharing on.
Yeah. So I'll start from the beginning. So there was one question from Sarjan. He was asking, can we use it for publications?
You mean the processing that you do on APEER? Yes, you can. You can mention it's done on APEER. And you can see that several of these engines that we use are standard engines. Like this rotate option is already an Image engine. So you will have exactly the same result if you did this on Image.
Okay. Okay, sir. Thank you. The next one is, sir, could you please show the workflow for measuring 3D parameters such as volume of an organelle?
Volume measurement. Let's see if there is. So as I was saying, this is not built like how you build Image with several workflows in mind. The idea is that people would contribute modules, to this platform. So let's see if there is somebody who has contributed a workflow for that. So let me come to that in a moment and explore the public workflows. Before that, I want to show you a few more things. So I will come back to that question on 3D measurements.
Yeah. So the last question is from Sajan. He's saying he tried with LSM deionizing ML prep train module. In result, it produced a blank image. Input was confocal TIFF image file. Can you show one with this module from your side?
Okay, could you repeat that question?
Okay. He tried with LSM deionizing ML prep train module. In result, it produced a blank image. Input was confocal TIFF image file.
Yeah. So the denoising part will be handled by Praseedha. As soon as I'm done with my part, Praseedha will show you the denoising part, and we will have some LSM images there. Yeah.
Okay. There are some questions in YouTube as well. I'll just read that out also.
Sure.
Rahul is asking, can we upload raw data or metadata in APEER?
Yeah, we can. So the way metadata is handled is as an image will be as it's handled by the image format. So if you're uploading a Zeiss CZI file, the metadata is embedded in the CZI. If you're uploading a TIFF file, it is part of the TIFF file and so on. So the metadata is not separately handled. It's handled as part of the image format.
Okay, sir. That's all for now. As and when a question pops up, I'll just read it out to you.
Sure. Thank you for that.
Okay.
All right. So what I showed you now is how you can run a workflow or you can open multiple instances. So let me show you something called batch processing, which will really show you the power of the cloud here. So I'm going back to APEER.com. I am going to open my workflow again. And this time I'm going to add several images. So I'll go to my APEER folder. Let me add eCell. So I'm adding, you can see I'm adding images in very different formats. I added a PNG, I am adding a CZI, that is Zeiss format, OME TIFF, normal TIFF, another CZI, a JPEG, TIFF, another CZI, a PNG, another TIFF, CZI, OME TIFF, maybe a couple more. CZI, TIFF, and a PNG. So yeah, I have maybe 15, 16 images here. So I say batch run.
Dr. Mathew?
Yeah.
Yeah, sorry. Somebody's having a trouble with getting annotation in 3D.
Annotation in
3D.
Okay, so the annotation tool is primarily designed for 2D annotations and not 3D, but you can annotate every frame in the image. So you have to do the annotations on, so if you click the 3D rendering application, so let me show you that in a moment. Let me come back to that as well, yeah? So,
yes, sir.
Yeah, so what I wanted to show you here is I had uploaded 15 images and now you see the 15 images are being processed simultaneously. There are only 3 pending. So at this point, and yeah, some of them are already complete. So the time it takes to complete one workflow with one image and one workflow with, let's say, 20 images don't scale with the number of images. It will be much shorter because these workflows are running in parallel. You see, some of them are already complete. Now, out of the 15, only 7 are remaining. Now, how many images or how many instances or how many parallel processing can happen? That depends a little bit on the resources available at a given point of time. Because it's a free platform, we have a common set of computational resources that are shared. So if there are too many people logged in at a given point of time, sometimes it can be slower. But if you really want access to multi image computation without any hindrance, that's a service that we can provide for a few. You see, most of those images that I uploaded, the workflow is complete. The images have been rotated. Let me go back to that. Sorry, I have to go to results, and you see we have all these results available here. So you will have several images processed. You can click on one of them, see how it looks like. See, the image was rotated. Okay, now since there were questions on data visualization, let me open another instance here. And let me see if I can go to my files and see whether I have a 3D data set. Or let me say Z stack. So this is a 3D data set that was acquired on a Zeiss confocal microscope with Eriscan. There's a data set with size of around 1 GB. But you see, we were able to load it quite quickly. Now what you see here is the 2D slice. I can navigate through the 2D planes. And if I want 3D, I can click 3D here. Now this 3D rendering is happening on a GPU-based server from Arivis. I can go to 3D settings. I can say I want maximum quality. And I can even change the opacity a little bit so that I can visualize it in the best possible way. Let's see if I can also do a little bit of histogram equalization. Maybe a little bit more. Okay, it has finished rendering, and you can see that for a 1 GB data set on the cloud, you see the rendering, it's pretty fast. I can rotate it in the 3-dimensional space. Now to go back to annotations, let me click 2D here. And as you're saying, you will have to do the annotations in 2D. I hope this answers the question we had before. If I can annotate this plane, then I can click here. I can go to another plane. And I can annotate there as well. So again, annotations happen in 2D and not in 3D. I think this is true for most, there could be some exceptions, but most image processing software, the annotations are usually done in 2D. We want to add a text. And I can say, okay. Now, another thing I can do is, once I'm done with these annotations, I can probably close this. I can go back to my viewer, open this again. And you see the annotations are there. Forgot which planes I annotated, but yeah, plane number 45 has the. Yeah, so the annotations are there. So once you annotate, annotations are saved as well. Now, what you can also do is you can go to your files, and if you want to share with this someone, you can share, creates a link. Let me see if I can share this with you right now. Let me see how I can access.
Dr. Mathew, there's another question. So
Yeah,
Snigdha is asking, so can we run more than one module at a particular time? Like, I have to rotate and also invert the image simultaneously? Is that possible?
Yeah. I will show you that if you are interested in that. I will show you how multiple modules can be connected in a short time. Just trying to see if I can send something on. Okay, let me see. So I'm requesting Praseedha to share a link with you guys.
If you want, you can mail it to the bioimage analysis also, and we can share also. If you're fine with it.
I think Praseedha should be able to drop this in the chat. So the image that I had in my files, now you can view this by clicking this link. Yeah.
And there's one more question on YouTube. Rahul is asking, these stats or live cell videos can be processed by APEER?
Yeah. We can process, let's say, time-lapse images and Z stacks as well. Again, each module is designed to do something different. So you need to see which ones are designed to handle that, and based on that, you can use that. Okay, so the next thing I wanted to show, and again, there was a question on how to have multiple, let's say, modules cascaded. So in this particular case, I'm going to add one more of this geometric transformation modules. So you see, I can add 2 or more geometric transformation modules. So imagine you want to rotate and then flip. I can go to parameters. Let me do it here. I can do it here. And let's say I want to, I don't know if you will see this. Maybe let's use translate. Yeah, so translate is probably easier to observe. Yeah, I'm giving it some, have to be careful on how many pixels I'm giving. Yeah, so I'm now rotating by 45 degrees. So in this module, when I say 45 degrees, that is accepted, but these 2 parameters are neglected because it is a rotate operation. In this module, I'm using translate, and which means the rotate input will be neglected and the offsets would be accepted. Again, I can say I want the output as a TIFF. I can give rotate 2. as the name of the output, and then I can see what image I have at the input. Okay, I have several of them. Don't want to run all of them. You see, this rotation and translation also happens for multi-dimensional data sets. So this is probably a multi-dimensional data set. Yes, it has a time-lapse image. So let's see if it rotates and translates the time-lapse image. So again, what this workflow is doing is it accepts the time-lapse image, it rotates it first, and then it translates. Sorry, Mridula, there was one question that I said I'll answer later, but I forgot what that was. What is now the unanswered question?
Yes. Is it there were two. One was please show us the workflow for measuring 3D parameters such as volume of organelles.
Okay, that's something I said I will search. Okay, anything else?
There was one about denoising, but I think Praseedha will take that question.
Yeah, the denoising will be showed by Praseedha. Okay, so the only pending question now is 3D measurement. So we'll come to that in a moment.
Yeah, also there is another question that was raised. Shall I ask that?
Sure.
Yeah. So, Bharti, they are asking, can APEER take raw files from any other format? Like, I think they meant TIFF from Leica.
Yeah. So again, depending on the module that was created, if it has this bioformats option, then it can. And let me search whether there is a bioformats converter. Yeah, I just wanted for this to finish before I go to the public modules and workflow. Just give me a moment. Okay, let me see if I think they are still running. Okay, while it's running, let me show you one final thing before we go to the public modules. Yeah. So this is something a workflow for each cell analysis. Where we will cascade at least 3 modules. Meanwhile, let's hope the workflow finishes. Oh yeah, it's done. Yeah, you see there is both rotation and translation. I don't know if you can see this. Maybe let me open this in another. So our workflow was supposed to rotate first and then translate, and you can see there is rotation and translation. Let's compare it with the original image, or let's compare all the images. This is the original one. This should be the rotated one. So this is a rotated one. Here you have both rotation and translation. All right, so that addresses that question. Now let me move on to the workflow I was building. So this workflow is called each cell analysis. So I will do it in 2 steps. First, I will do segmentation. Then I will do analysis. Now here you see this module number 3 needs two inputs. One input comes from the previous output, that's output for cell segmentation. And the second input is the original image, which means this has to come from module number 1. So the outputs need not always come from the immediately preceding module, but it can also come from any module in the workflow. So in this case, I'm going to loop this wire behind this and connect it here. So this input came from module 2 and this input is coming from module 1. So let me search for an appropriate image. I have an eCell image. Let me see if I can share this with you. So if I want access to my data, I can always go to my files and I say eCell. It's my PNG and I can click here and say download. So this is now available. Again, I will share it with Praseedha so that Praseedha can then share it with you. I drag and drop here. So my workflow is still running. Oh, let's see if it is done. Still running. Okay, and it's done. So this was my workflow. This is my original image, each cells. Here you see there are two types of cells, one that is stuck and one that is floating. The next step was segmentation. So this is a segmented image. I hope you have got access to that image. I'll show how to build this workflow again. So in the third step, you see the segmented image or the segmented outline is overlaid with the original image. And that's why we had to feed it the original input. And there is also a PDF. So PDF cannot be visualized, so I have to download the PDF. And the PDF is has its histogram area versus number of cells. And this is the data from the output of this workflow. Now let me go to the public workflows. So this, what I showed you now is how to build workflows using either your own modules or modules that are available as public modules. Let me go back, or maybe let me open another instance. And here you see you can explore all the public modules. So as I showed you before, there are two ways in which you can access the public modules. When you create a workflow, again, let me repeat that workflow creation process for those of you who have gotten the image just now. I said I want.
Manoj, just a moment. Actually, I've not been able to share. So let's check with Akshaya how to attach a file.
Can you just send it to the mail ID? We will
Okay.
share it with you. Yeah.
Sure, sure.
Okay, anyway, let me show you how to build the workflow again, and then we can, at the end, we can append the image. I'm calling this, so, okay, maybe start from the beginning. Create workflow, give it a name. We call it analysis 2. I click on the plus button here. I say I want eCell. So I'll start with segmentation first. Then I click the plus button here and I say I want cell analysis. This requires two inputs. The first one comes from the previous module, immediately preceding module. And the second input comes from the output of the first module. So did we get the image? Tula, were you able to get the image?
We still haven't received the mail.
Praseedha, did you manage to see?
I just mailed it to you. Actually,
Okay.
yeah.
I think it'll take a couple of minutes.
Yes.
There is some problem with the network as well. So yeah, we'll share it.
Once you have that, what you could do is drag. So if it's in your downloads folder, drag it from the downloads folder into the input files. And that uploads the image. And once the image is uploaded, you can click the single or batch run. Now there is another feature here. If you want to do it one step at a time, you don't want the entire workflow to run. You want one module to run at a time. Look at its outputs and then decide whether you want to run the next module. It's like a little bit like a debug mode. Then what you can do is click on this little arrow here. And it gives you two options, step-by-step run or single batch run. Single batch run is default. Let's do a step-by-step run. Step-by-step run means it will run one module at a time and then wait for us to say, execute the next module. So it's running the first module, the input module. So here it's waiting for me. Unless I say run next module, it will not run. I can observe the output. Okay, I think the segmentation is fine. And then I say run next module. This is a step-by-step mode. All right, now let me go to the last part of my part of discussions, that is using the public workflows. Again, let me open another instance here. I click public workflows. So public workflows are workflows that are created by several users and uploaded to the they're made public. And here you can search for several interesting workflows. Let me see if there is a 3D option. The 3D co-localization analysis. There is object tracking. So there is a segmentation. There is a tumor blood vessels analysis. There is a 3D segmentation workflow. Let me see if it works. whenever you open a let's say public workflow, it creates a copy of the workflow because you don't want to edit a public workflow. So it will create a copy of the workflow which you can then edit. So the original workflow on the cloud, on the shared public repository, remains unaffected. I can always view what the data set is. So what I did was I went to the first module, I clicked on this I button that opened up the data set. I can see how it looks like. And say 3D. And this looks like they are 3D nuclei. Sorry, Z stacks of nucleus. So let me then go back and see whether I can run the workflow. While this is running, let me open another instance of APEER and search for a cell counter and analyzer workflow. So in public workflows, usually the image is already provided. So the test image is available. So I'm going to cell counter and analyzer. I'm opening a copy of the workflow while our 3D segmentation workflow is running in the background. You see, this is a rather complex workflow in the sense that it has 1, 2, 3, 4, 5, 6. Yeah, 8 modules. The first module is an OME TIFF converter. So this is, the question came, can we use any module or any file format? So for most file formats that are available, including some of the standard microscopy file formats from Leica and Olympus, this OME TIFF converter will convert it to an OME TIFF. So if the module is designed to work with OME TIFF, then the workflow can be run here. So which means this OME TIFF converter makes the workflow quite gentle. The next module is an 8-bit converter. So if your image can be in any bit format, for many processing functions, you want it in 8-bit. So it's an 8-bit converter. Next one is an auto contrast. This is a contrast enhancement module. The next one is auto thresholding that does the segmentation. There is a fill holds module, which is a post segmentation processing step or a binary processing step where any holes in the segmented object is filled. There is a cell filter that tells you what kind of object you want to select, what morphology you want. You can select that. And finally, there is a cell reporting. So here, let me upload one of my files. So I go to my APEER folder. I say I want time series data because this is cell analyzer over time. So it is analyzing a time series. And let's take a look at this data first. So you can see that here it's a time lapse image. You can run it. Over time, you see there is some cell death happening. So the shape of the cells or the nuclei in the beginning is quite round. Then they become a little bit irregular. And finally, when they are really, if they're really dead, it becomes dense and it becomes rather circular again. So if I were to see the morphology of cells, the morphology is initially quite circular, then it becomes irregular. And finally, when it is really condensed in its final stages of cell death, it becomes circular again. So you can see, if I were to plot the number of cells with high circularity, you should probably see the number of cells decreasing and then increasing. So the circularity of these objects decrease and then they go up again. So let's see if we can find that. So all my modules are green, which means all the parameters are either selected default and there are no specific inputs to be provided. So the second module is OME TIFF converter, no parameters required. Third module is 8-bit or converter, and again, no parameters required. There is an auto contrast with a cutoff of 0.1. I will leave it at that. Then auto thresholding, OTSU is a very good choice for this kind of fluorescence images, so I will leave it at that. Fill holes is not taking any parameters, and one I want to change is circularity. So I want to see how, if objects that are highly circular, what happens to them. So I'm selecting circularity between 0.5 and 1. So those objects which have a high circularity, what happens to them? So you should rather see the number decrease, because as they die, they become irregular, and finally at the end of the death, they would become more circular because they are so condensed that you essentially have a circular shape. So let me run this. I can open another instance of the same workflow. Let me open up here again. I go to public workflows. I say cell analyzer. Open workflow. And let me give one of my inputs. So there is a default input, but here I prefer to give one of my inputs. Time series. Now in the second workflow, I'm going to do the opposite. The first one, we were looking at what happens to objects that have a high circularity, 0.5 to 1. Here, let me try what happens when to objects that have a low circularity. So this one, we might expect that the number will go up and then it will come down. So while this is happening, let me look at all my workflows. So there is a 3D segmentation that was running. That is still running. Cell counter analyzer for high circularity is running, and cell counter analyzer for low circularity is running as well. So while this is running, if you have questions, I can take some questions. Praseedha, are there any more questions?
Yeah, we have one question from Neha. Can you hear me?
Yeah, I can.
So Neha is asking, can we also add the workflow to count the fluorescent spots in segmented E cells?
Fluorescent spots in segmented E cells. Again, I'll have to search if there is a specific workflow for that. Again, as I was saying, the idea of this platform is that people can share, and then once shared, other people can use. The idea is like it's more like Wikipedia at this point. And it's not really to provide standard software for specific applications. So if somebody has shared a workflow like that, we will always have it available. So let's probably search for it. And as people keep adding more and more workflows almost on a daily basis, it's not possible for for someone to know what exactly is there on the platform on a given point in time. Every day something would change or something new gets added. So you said puncta, right? Let me call it spot or blob. Yeah, it doesn't look like we have a workflow yet for that. But if you know somebody who has segmentation, no, we don't have puncta tracker. So if something is not available as a workflow, you might want to search the public modules, but then you'll have to build a workflow. Blob. There is a blob tracker. Yeah, there is something called blob detection. Yeah. So this blob detection might help you to detect the fluorescent puncta, I believe, but you might have to test it out. Any more questions?
There's one question on YouTube. Rahul is asking, can we draw a line for pathway of single molecule localization in live cell video by using annotation tools in APEER?
Oh, you are saying single molecule tracking on a manual way by using the annotation tool. Yeah, that should be possible.
Okay, sir.
So,
Thank you.
so as I was showing, let me see if I can. Let me open another instance of APEER. But yeah, I'm wondering how that will come out, because annotation is not really designed to give you. So usually for cell tracking, what you need is one final image where the track is clearly shown. But here you will have these annotations on every single frame. So I don't know if that would practically solve the problem, but anyway, let's take a look. I can do it probably on this one. So I can start with image number 1 and annotate something. And in the, okay. And in the next frame, I will then have to do it again. It has moved. I can annotate it again. Go back. Third frame, it has moved again. Okay. Yeah, so I think at the end of this process, if you here you have 65 frames, if you put this annotations onto 65 frames, you will have to export the annotation as an image and then probably put these or add these images up to kind of get a track. Yeah, I've not done this, but I think it should work. The idea is in every frame you put some annotations, download the annotations, and then do something like maximum intensity projection or something. And then you'll see the probably one image with the tracks of that particular cell. I don't know how elegant that is going to be, because in fact, we have a tracking workflow. So if you go to, but I'm not sure if that works for single molecules, but for cells, definitely it works. On public workflows, we have a tracking workflow. Okay, let's see how this one works. Let this run. In the meanwhile, we have some it's still running. Okay, my cell counter and analyzer is done. This is my graph. Yeah, as expected, for high circularity, you see the circularity decreases first and then increases. So this is the next one. And if I change the criteria, you see the circularity increases and then decreases. So kind of have the expected behavior for the number of cells for a given circularity. My 3D segmentation is taking a little bit longer. But again, you can always try this. The good thing with workflows is they all come with an input image. You don't need to provide an input image separately. You can just go and try it out. So I think my allocated time is coming to an end. Are there any more questions? If not, I would like to hand it over to Praseedha.
Dr. Mathew, there are more questions in the chat box.
Okay. Could you read it out to me?
There's one on YouTube. Sure.
Yeah, Mridula, are you there?
Yeah, sorry, there is some connection problem. And my colleague Akshay will just ask the question.
Dr. Mathew, am I audible?
Yeah, I can hear you. Sorry, just a moment. Let me stop sharing and let Praseedha start the sharing. Praseedha, could you start while I answer some questions?
Yeah. So the question is, can't we use the same circle having the same area in every frame?
Yeah, we can. I think I can just copy and then paste it there. I believe I could do that. Let me see.
So before Praseedha's session, maybe we can take a break till 15:45, 3:45. Is that okay?
Yeah, sure. I think.
Sounds good.
Yeah.
All right. So then, thank you everyone for joining this session with me, and then I hope what we were able to present today was useful, and we'll hear more from Praseedha. Yeah, thank you so much.
Thank you so much for joining, Dr. Mathew. We look forward to Praseedha's talk. So all the participants kindly be back by 3:45. So we will start with Praseedha's session. Hello, Praseedha.
Yes.
We can start.
Okay, thanks. So, hi everyone. Thanks for joining the session. So now let's get started with the denoising modules in APEER. Let's have a hands-on session on that topic. So as you all know, denoising is an important image processing step. And especially to extract useful information from noisy images, it's quite crucial, especially for research applications. So let's see what are the available options in APEER. So for that, let's go to the public modules. I hope like most of you have access to APEER now. So let's go to public modules. And we can search for denoise. So these are the various options for denoising on APEER. In this, these two, that is the total variation denoising and the non-local means denoising, they are traditional denoising approaches or based on traditional image processing algorithms like total variation and then Gaussian filtering, median filtering, and so on. So as most of you may know, these kind of traditional image processing denoising algorithm works best when the noise is random. And also most cases you need the noisy image as well as a clean target image for these algorithms to work. But today's our topic of discussion is denoising algorithm using machine learning. So you can try these two out later on. So today I'll be focusing on denoising using machine learning. So in cases where you have more structured noise and also you don't have a clean target to compare to, you have only noisy image at hand, then these traditional approaches don't work. In that cases, machine learning approaches come to your rescue. And these other modules, the LSM denoising pre-trained that Sajan was mentioning before, then the denoising training and inference modules, the denoising ML pre-trained, AI image denoising. These are the currently available public denoising modules based on machine learning on APEER, and they are adding more in the list. So let's get started with the first one, LSM denoising ML pre-trained. So as the name suggests, it's based on machine learning based algorithm. And what it does is it creates a pre-trained model. It uses a pre-trained model which has been trained on a lot of LSM images or confocal images. So the APEER experts have already created a machine learning model using by training them on many LSM or confocal images. And you just have to provide your noisy input image, and this a pre-trained model will help you to denoise your noisy input image. So let's get started. So first you can open the module. So you get, as Manoj mentioned, you have a brief summary of the module on what algorithm it is based. This is based on noise to void machine learning algorithm. It also shows you a brief description of the module and what are the input formats that it supports and what are the output formats and other such information. And suppose you're interested to download the code that's also available for this module. So currently, let's get started with executing these modules. So as Manoj mentioned, we always execute modules by creating workflows. So let's create the workflow. So first, you can provide a name for the workflow. Let me give a name similar to the module. And as Manoj earlier mentioned, there are existing text files in the module. So for now, you can use that when you're doing the hands-on session. Or if you already have some LSM samples at your disposal, you can use that too. So let's create now. So when you create a workflow for an existing public module, this is how it appears. By default, it has a workflow input and the module gets selected. So for this workflow, that is LSM denoising using ML pre-trained, it just needs the input images to be fed, the input image that you need to denoise. So in this particular example, there is already an image, test image. So for now, you can use that. Let me also try to do a batch mode by adding one file from my end too. So I have a mitosis image, one time slice of that to demonstrate. So maybe I will just show you the image. So you can see it's a noisy image, and this is what I want to denoise using my LSM pre-trained machine learning algorithm. So we have two images. So let me run this in the batch mode. Okay. So my workflow is running, and let's wait for the results to appear. I hope you are following right. Am I fast enough, or just let me know if there is any feedback?
You're fine, Praseedha.
Okay, okay. Thank you, Akshaya. So here it shows the status that I have one running workflow. Let's wait for a couple of minutes. Okay, I think maybe since many people are actually okay, I think it's finished. Usually when more people are logged onto the cloud, sometimes it may get delayed. Okay, so now it is the workflow has finished successfully, and you can view the result. So you just have to click see results, and it will automatically navigate you to the corresponding workflow results page, and you can see these were my inputs and the corresponding denoised outputs are there. So let's just compare our results. So let me compare with the mitosis sample. So this is, as Manoj mentioned, the Arabis web viewer. So let me open it. And also the denoised one. Okay. Let me just improve the brightness a bit. Okay, let's just compare this two before moving on to the next denoising module. This is the input. Okay, and this is my output. So this is like a side-by-side comparison, and you can see that the LSM denoising pre-trained, that algorithm has done pretty good job in denoising the input image. So you can try out with different samples at your end and try this algorithm. So this works with, this is pre-trained with LSM confocal images. So this work with LSM noisy input image. Now let's move on to the next denoising session. So we did LSM denoising, ML pre-trained. Similarly, there is something called EM denoising, ML pre-trained. So this is similar to the LSM denoising module, but here the ML, the machine learning model has been pre-trained using EM or electron microscope images. So if you have electron microscope images, you can try this out. And there's also a test image. I think since we are limited on time today, I will skip for the time being. You can just try it out at your end. And there is another one called AI image denoising. This is also using a pre-trained model. But the algorithm it uses is different. So these two actually uses something called noise to void machine learning algorithm, while this is something called a noise to noise algorithm. So if you are interested, you can read more about it. And in the image or in the module description also, there is mentioning about what algorithm it is based on. So next, let's move on to something interesting. So these are all pre-trained networks or pre-trained models, and then you just have to provide input images to get your denoised output. Suppose you have a set of images which you want to train your own machine learning model for denoising. APEER provides that flexibility too, and that is done using these two modules. First, the denoising ML training, where you provide a set of images. It can be LSM or EM. It should be a set of images called training images. And you train a machine learning model using those set of images. And then use that model to denoise your image using denoising ML inference module. So let me show you how we go about it. So let me open this module. So it provides a brief introduction into what it is about. Again, it's based on noise to void algorithm, the description and the inputs and output and what are the parameters it has. These are all like machine learning hyperparameters, which you can read about if you're interested. And now you can create a workflow for this, for creating a machine learning model based on your set of input images. So for this, let me try to use the mitosis full full set stack to train the model. So I'm creating a workflow for this. So I have to provide the input image. So for training, you need a lot of images, not just one. If you like provide more number of images, your training model will be more accurate in your denoising outputs. So let me provide cell mitosis set stack image. This is acquired using Zeiss LSM microscope. Let me just show you the image. Okay, so it has like set stack and time series combined. So you can view it in 3D. So this is a cell mitosis happening. So that is my SAM input images for training the denoising model using machine learning. And next, this is the module for machine learning training. And there are like a lot of parameters. So if you click here, these are all default parameters. So if you're interested, if you read more about machine learning approaches, you can try to modify these and use them in your model. So for now, I'm keeping it default. And let me run it. But unfortunately, this I cannot show you live because machine learning training involves a lot of, like you saw, a lot of parameters, right? They are called hyperparameters, and actually it involves training a lot of hyperparameters, and it's quite time consuming. But you don't have to worry because nothing is happening locally. Everything is on the cloud. It won't be eating up any of your resources, but it will take time for the model to be generated. So to show you, I have pre-run this workflow and I can show you the result. So before that, let me just explain to you what we are going to do here. So I told you we can create our own model and use it for denoising. So you can see these are the input images for training, and then these are the outputs. So you can see there's something called train model weights. This is train model configuration file. So these two are the ones that has to be fed to the denoising ML inference, which will actually provide the denoised output. So once training is done, you can download these two outputs and then use it as the input to the denoising ML inference module. So maybe I will show you the result. If it's too confusing for you, it's okay because there's a shortcut to this. There is an existing workflow which actually combines these two. But if you are interested, you can do it separately and like get a more feel and insight into the denoising ML training and inference. That's why I just touched upon this. So for now, we are doing denoising ML training, and the results for a prior run, I can just show you. So you can see there is something called the configuration.json file and the weight file. So these are the inputs that has to be provided to the denoising ML inference module. Okay, is it okay so far? Can you hear me?
Yes, we can hear you.
Yeah, okay.
It's fine.
Yeah, okay. So now, once the training is done at your end, when you actually try to use this module and train your images, after this is done, these two outputs has to be downloaded. You can download it and then you can use it in the next module. Okay, you can see it requires the input images, the train model weights, that is the .h file, and then train model.configuration, that is the JSON file. And you have to provide the noisy input image that has to be denoised. Okay, so I think it's, I don't want to further confuse you. Instead, I will just show you there's a public workflow for this complete thing. You can just search for denoise. So you can see there's denoising ML end-to-end workflow. If you open up, so there you just have to provide your input image, and then the denoising ML training module and denoising ML inference is already connected. So you don't have to worry about it. So you can try to train your own denoising ML training models and then get denoised output from this module. Okay, since this takes time, maybe you can try it out at a later point of time. But if there are like any questions, you can always get back to us. So this is one thing in denoising. So I think denoising session we have covered. Just a brief recap. So in the public module, we have many denoising approaches listed. These two are based on traditional approaches and the others are based on machine learning approaches. So by machine learning approach, we just mean that we train images, we train a model, machine learning model of using set of images, and we use that model for denoising. And these are all pre-trained network for which you just have to provide a noisy input image to get a denoised output, while these two require you can combine it in this public workflow called denoising ML end-to-end workflow, where these two are actually combined. The denoising ML training and workflow are combined. So yeah, this one. So this is quite powerful because you can use your own input images to train and then denoise your input images. So that is the end of the denoising session. But we have one more section to handle, that is how to use machine learning for segmentation. So are there any doubts in the denoising section?
There is nothing in the chat box, but if any participant has anything, they can either unmute yourself or they can still type in the chat box.
Okay.
You can go ahead, proceed.
Yeah, maybe I can go ahead then. So next is, so right now we saw how machine learning models can be used for denoising. And APEER also allows you to use machine learning for segmentation, and it provides an easy user interface to do that. So this session, this is a dedicated tab. This is for machine learning for segmentation. So segmentation, as you know, it is like partitioning a digital image into different segments based on certain criteria. So we already have standard segmentation approaches like thresholding, watershed segmentation, morphology-based segmentation. Then why do we need machine learning? So the answer to that lies in the input images that we use. So this is an example I want to show you. So this is a tissue of hippocampus region of the brain, and it's taken from an electron microscope. So you can see, suppose you're interested to segment the mitochondria from this sample images. It's actually stat image. If you use traditional pixel-based thresholding-based approach, this is what you get. Okay, that is, it segments mitochondria, but also segments the cell walls. Why? Because you can see the contrast levels as well as the intensity levels of mitochondria is quite similar to the cell walls. So in such images, the traditional segmentation approaches fail, and then machine learning actually comes to your rescue, and APEER provides quite a user-friendly interface to do that. And I think Manoj already touched upon this topic a bit. Like, it has 3 sections called annotate, train, and segment. So annotate, okay, in the overview session, it shows what each of them is. Like, annotate is you upload your images, annotate or label the images, and then use it for training in the next section. And in the train one, you're using these annotated images to train a machine learning model. And finally, the last section is segment, where you use this machine learning model to segment your input images. So let me try, if you have some images, you can try along with me. So let me go to annotate. And if you have a new data set, you can just click here, add a new data set. So type mitochondria data set. So it will ask me what kind of segmentation I want as my final output, whether it's semantic or instance. And it also clearly explains what each of them is. So semantic is nothing, it's pixel level classifier. Like, suppose in an image, there are like cats and dogs. It will classify cats and dogs, like it will classify globally. But suppose you want the instance of each class. If you want pixel classification along with object detection, then you have to go for this segmentation and separation. That is called instance segmentation. But usually for most microscopy applications, this is what we use, semantic segmentation. But suppose if you want to use the instance in any application, you are free to go ahead with that. But one thing to note is that it requires larger amount of data to be annotated, because you need the information about each object, and also it will require more time as well. So let me go with semantic now and press next. Okay, since I already have a data set by the same name, it's not allowing me to create. So let me just create. And I choose semantic. Okay, and now I can drag and drop or select my APEER files. So I already have my mitochondria set on my APEER, so I can just use it from there. Okay, I think. Okay, I think maybe I will just upload it again. add images and then browse. So this is a set stack of the mitochondria sample. So once the image is loaded, the annotate button becomes active and I click it. So another window opens up, the Aribis web view, and it gives a short walkthrough animation of how to actually do annotation. So let me actually show you that now. So I close that. So you can see here the image. You can actually view the set stack using the slider. You can move to each slice. Or you can also use this panel, this side here, to individually access the set stack, each set slice. So by default, there is something called background class, and you can create your own class. So suppose I'm interested in mitochondria class. I create a class called mitochondria. Press OK. And now suppose I want to change the color to something else. I can do it here, edit, maybe I pick blue. So now whenever I color, do something, some coloring for mitochondria, it will appear in blue and the background in purple. This also you are free to change. And if you want to delete a class, you can do here. And you can add more classes if you want. You can add a cell wall class if you're interested. And okay. So there's like a restriction on how to use the cell names. Okay, there should be no space. Okay, even under okay, no space and no special characters. And okay. So I just created like a cell wall class in mitochondria. And now suppose I have to annotate or label the mitochondria class, just like Manoj showed in the annotation for the other examples. There is a paintbrush, there is polygon and rectangle tool, and there's also an eraser. So suppose I use the paintbrush to annotate the mitochondria, and I can use the mouse button actually to zoom in and zoom out. And I can also use the mouse to like pan different areas of the image. And let me annotate mitochondria. Okay, so this you can see there's autofill option here. If this is like unchecked, then if you are interested in some like ring shape structures or donut shape structure, like it will be like empty in the middle. But in this case, I want it to be filled. So let me do this. And if I make some mistake, I can use an eraser to erase. Okay. And then enter. So you can see these in the mitochondria class, there are two objects that are already annotated, and that will be used for training. And similarly for the cell wall, you can annotate. In this case, you can maybe here, you can adjust the brush size. You can adjust. And you can maybe draw this cell walls. And then again, and you can annotate more objects. And background, you can always color maybe bigger size. I can just color around this, and it will automatically crop. If I enter, it automatically crop to the outside of the object. Is that okay so far? Okay, I hope you're following. Shall I continue? Is it okay so far? Okay. Akshaya, can you, and Mridula, I hope I'm audible, right?
Audible.
Yeah. Okay. So I hope so far it's okay. So we create classes, we annotate them, and suppose you don't want to you want to hide your annotation, you can just click here. If you want to do like more annotation and these are like distracting, you can do that. And similarly, the labels, if you are not interested to see the labels, you can hide that. And yeah, that's about how you annotate. And once you annotate, you can tick mark this. So that means when you tick mark, only that image will be used for training. Otherwise, the images that are not ticked won't be used for machine learning training. So after you finish one slice, you can go to the next slice and similarly annotate for this. I think this is the background. So let me click the mitochondria class and then annotate. And if you do more annotation, your machine learning model will be more accurate. So for now, I'm just showing how to annotate. So since this is time consuming too, I've already annotated and kept, but you don't have to worry that you don't have to do everything in one go. Once you do something, it's saved on the cloud and you can come back at a later point of time to continue annotation. Okay, and so on. So let me show you the already annotated one because it will be time consuming to annotate it live now. So in the annotate section, in my data set, you can see all the data set that have already been annotated. So you can and sometimes when you open this array-based web view, you will get an error like your window resolution is not enough. So in that case, you can just adjust your zoom level. Like if it is more than 100%, this error will appear. So you can just adjust your zoom level. Okay. So like I have like 165 slices, but I have annotated around 12 slices. So you can see I've just annotated for mitochondria and the background. So I've annotated 12 samples. And so you can try out with different samples at your end as well. And then you can train. So the first step in machine learning based segmentation is annotation or labeling the images. It's just straightforward, just using paintbrush. And you can also use polygon tools like Manoj mentioned. So maybe I will show you that. So suppose I'm interested in annotating the background with a rectangle tool. So you can just go ahead and do that. And similarly, polygon too. Just a minute, okay. So, but if I'm not interested in using this for training, I don't tick mark. Otherwise, I can tick mark this. That's it. And then the next step is train. So it will first check whether all your annotations are like in proper format, which is compliant to the APEER website. So it's checking that. And then when I start, it's actually adding the annotation to the data set, creating a labeled image. And then I just have to start training. So again, you have to give a name to your training. So let me give. So it asked me which annotated data set I have to use. So this is the one just I showed you now. So I haven't annotated it fully. So this is the mitochondria data set I've annotated. So I'm using this, and then I press next. So here you can, again, if you want to change your annotation, you can do. So if I'm providing semantic, and these are the classes you want to train. So both background and mitochondria. If there are more classes, you can choose between, like, if you don't want to train for one class, you can just untick it. But for now, I have just mitochondria and background, so I keep both the classes. And if you are using Sen software, actually you can use this ML model in Sen. So you can tick mark it if you want. Otherwise, you can just use it for segmentation directly on APEER. So, and one thing is, it also emails you, send you an email to the registered email once the training is finished. So I start new training. So you can see the training is in progress, but you can see it will run for a maximum of 24 hours. That's why that email functionality is important, because it will email to you once the training is done. This is because the training process involves training and modifying, fine-tuning of millions of hyperparameters for deep neural networks. So this will take around maximum of 24 hours. So this is a time-consuming process, but you don't have to do anything. Everything is done by APEER on the cloud. Okay, you just have to annotate your labels and put it for training. So overnight, if you put, the next day you will get the training results. So once the training is done, the next step is use that training model for segmentation. So since this will take 24 hours, I cannot show you live again. So let me just show you the results of a previous run. So it's a mitochondria set stack, segmentation training. So this is one of my previous trainings, which I did for the same set stack. And you can see, okay, so this is my input image, and there are like many inbuilt modules which you don't have to worry about for now. And then the results. So for now, if you have Zen, you can actually use the CZ model. This is the CZ model is specific to Zen machine learning, so you can use it. And if you want to use this in Python, suppose you don't want to segment on APEER with this, suppose you want to segment using some other like Python code, then you can download this and use. So for now, let's try to segment this on APEER itself. So for that, in the train session, I can see my trainings. So mitochondria set stack training. So the next step is segment. So I gave again a segmentation name. And here I can select the model. So select the model that I've trained before and the images that I want to segment. So let me. So that I trained using the training set stack, and I'm testing the segmentation using a testing set stack. So once the image to be segmented is uploaded, you can save. And then you can start segmentation. Again, it will send you an email once the segmentation is finished. So again, it is in progress, and again, it shows it will run for maximum 24 hours, but usually segmentation is much faster than the actual training. But once the segmentation is done, it will send you an email. So that is the segmentation. So let me also show you the results of segmentation, because it cannot be done live. So okay, so this is a semantic segmentation where I get the global classes. So I can see the overlay here. You can see the various, okay. So mitochondria set stack segmentation. So we have the input is the input testing set stack, and this is the ML prediction or the ML segmentation output. So there are like CSV files which show the information about each object, and this is the prediction or the binary file, and this is the overlay. The input image is overlaid with the binary mask. So this will show you how good the segmentation, how good or bad the segmentation is. So let's see the output. So this is my, like, if you can see, there are like blue color, that segmented output. You can see still there are like some spots where it has not segmented properly. So because since I'm only segmented 12 out of the total 165 slices. So if I'm able to segment more, because this is quite a tricky sample with very low contrast difference between different cell organelles. So but still it manages to do a better job than the basic segmentation step. So you can play it to see how the segmentation in each set slices. So there are like some points where it predicts or predicts wrongly, like this areas. And you can also watch this in 3D. Because this is the blue color is not quite visible though. Okay. If 3D is more like convenient to you, you can use that, or you can use 2D. So this is semantic segmentation. So all the mitochondria is represented by just one color or one class. So I also, for you, I've tried instant segmentation for this as well. So let me show you that results also. So it is mitochondria segmentation instance. So instant means it will help me to do the classification and object detection as well. So let me see the overlay. So you can see each instance of the mitochondria is segmented like separately, which is not at all possible using this basic threshold thing, because you can see like all the mitochondria samples are like the same contrast and intensity levels. So that is instant segmentation. So yeah, that's it about the machine learning for segmentation. So you annotate or create labeled images, use that to train, and then use a trained model to segment. So yeah, training and segmentation takes time, but everything is happening on the cloud. So you can just give it to train and segment and come back the next day to view the results. So yeah, that's it about the machine learning for segmentation. So if any questions?
Yes, Praseedha. There is a question in the chat box.
Okay.
Can we get the output for the different mitochondrial morphologies, like hyperfused or fragmented form?
Can you repeat the question?
Sorry. Can we get the output for the different mitochondrial morphologies, like hyperfused or fragmented form?
Okay, from the machine learning segmentation. Okay, actually, I'm not aware of that much. Maybe I will get back to you on that question after discussing with Manoj. So it's in the chat, right?
Yeah, it's in the chat.
Okay. Maybe I'll get back
It's
to you.
from Gunjan, and yeah.
Okay, let me just note that down. Gunjan, right? So will we have access to the chat after the meeting is over?
Yes, we do save our chat, so
Okay. Otherwise, we can
send you the.
reply via the email, right?
Yeah, sure.
Okay. I will reply to this question. Okay. So far, from my understanding, we can segment, but these are like post-processing steps. But I understand, if I understand correctly, like the morphologies, this will be the post-processing after segmentation, right? So I believe we need to add more modules after the segmentation, but I will confirm with Manoj before like I confirm the answer.
Sure. And we can send the answer to
Gunjan, right?
Yeah.
Yeah, sure. So any more questions?
There is none in the chat box, but if any participant wants to ask, they can directly unmute. Anyone? No.
So I understand like these are like this most of the things you couldn't do it live, so it might be a little bit intimidating, but if you go and try out with some sample images, I think it will be like worthwhile, and you can always come back to us with any questions you want. So I think this part especially you cannot do it live. That's why I did some try runs. So if it is like confusing for you, don't worry. You can always try it out at your end. And this is free for like I think all of you, the APEER platform. So and there is 100 gigabytes of storage as well. So you can upload your images and try it out any time.
Sure. And thank you so much for sharing this APEER platform with us. We have been using it in the lab and it works great for us.
Okay, nice to know that actually.
I guess there are no more questions. Thank you so much, Praseedha, for joining us today.
Yeah, sure. Thanks for inviting me to. And
okay, so if you're done, you can unshare the presentation so that we can have a session screenshot.
Yeah, sure.
And I would request all the participants to switch on their webcam.
Is it for one final time?
Akshay, can I just inquire Manoj to join too? I think he is not.
Yeah.
Just a minute.
Hello, can you hear me?
Yes, sir, we can hear you.
I was saying we are all coming on for the one final last, and there's somebody photobombing. That's nice. So I must say that when we started, we were not sure how the response would be and whether this will be something that anybody would be interested in. But actually, we are floored by an overwhelming response, and this was primarily done against all odds. My lab suffered, I would say, trying to make things automated. I feel that when we do all these experiments, the bottleneck actually is not doing the experiments, wet lab experiments, it's just sitting with the data and analyzing it. If I finish imaging today, and I think it's true for your supervisors and other labs as well, that you don't know when you'll get to see the graph, So, and then you keep on doing more experiments and you do more microscopy, and then data accumulates, and then you don't know what is happening, right? And so that prompted me to actually collaborate with Lakshmi for a while. And we said, why can't we develop pipelines and things like that? And after a year, I realized it's not so easy. We need to really keep ourselves educated all the time, and the students need to learn. They still need to do experiments. And I thought this kind of workshop would be very useful. So as you can see, the whole workshop was done by my students. I'm no expert in any of these things, but it's always a wish list. It has the field has moved from taking pretty pictures to really making sense of what we are seeing. And I think if you analyze it properly and look at it, maybe new discoveries can also be made, not just look for what we want. And so I hope this message reaches out to everybody that the recordings will be available, and if this works out this way, that hopefully with some support from funding and all, we will be able to do it. DST, we wrote a grant and we got selected for it. It was, I think, for a workshop. And although as usual, the funding was cut more than 50% or 60%. And with all the COVID restrictions, we still managed to do this. But this is one kind of workshop that we can always do it, I hope. And whatever lessons you have learned from here, I hope you'll use it and pass it on to your lab members and create an environment where, a right kind of analysis can be done and more interesting data can be plotted out of all that. Okay. And including today's speaker, who spent a lot of time and efforts in explaining everything, I would thank all the speakers and all the participants for, except Saturday, I guess some of you nicely bunked it, I know, but for being patiently sitting and learning. This is taxing. When you're sitting and learning so much, it's not just listening to talks in a conference. Therefore, we spaced it out for such a long time. If you had 2 or 3 of such sessions every day, you can imagine it would have been very difficult. But nevertheless, I hope it was enjoyable for you and you learned a lot. And my students, what they've done is they've put together a feedback form. I don't think we have shared that with them yet. So you would be getting a feedback form. We will make one for the speakers as well, separately at some point of time. And we'll share that. Please feel very free to write whatever you felt about this workshop. It will give us a lot of perspective and perhaps encouragement also, and the courage to go ahead and conduct maybe one more meeting like this in the coming time. So good luck to all of you in your research. Do well, and thank you so much for being a part of this workshop. And I would also like all of you to join in actually thanking my lab students who have taken whole 10 days off and sat there and doing. Okay, so let's give a round of clap to all the people who taught and also all the students who organized this as well. Thank you. Okay, so should we give our biggest smiles yet, or have we done that? Okay.
As big as possible. And we have circulated the feedback forms. So it would be great if you send us back at the earliest. Okay, we can take a screenshot. We are done. Thank you so much, guys. Thank you for joining.
All right. Take care, everybody. Stay safe. Bye.
Thanks, everyone.
Bye. Bye, Lakshmi. Bye.
Bye, Ravi.
Thank you, Guru.
Special thanks to Akshaya, Ruchika,
And Ruchika,
and Aarti, everyone.
Yeah, if I start counting, I know I'll keep on.
Yeah, all your lab members, Ravi.
Yeah. No, Lakshmi, it was wonderful to have you. Without your support, you wouldn't have done this part. It was nice.
Okay.
All right.
Yeah. See you guys.
Bye. Bye.
Bye.